We begin chapter 14 on solutions and their behavior with a potentially tragic story about a survival at sea. And the reason they survived, because of their being well prepared to abandon their boat and take a fishing line with them, but to also take a portable reverse osmosis water purifier with them. We're going to be talking about what reverse osmosis means in this chapter. Meanwhile, we have some vocabulary words we've got to take care of. Since this chapter is on solutions, we are, of course, going to ask the question, first of all, why do we devote an entire chapter to solutions? Well, if you think about it, your blood is a solution, oceans are solutions, the atmosphere is a solution, many of the beverages we drink, unless it's absolutely pure water, are solutions. There's so many different kinds of solutions. Medicines are often given to us in solutions. Think of IV solutions. So solutions are all around us and in us. What is a solution? Remember that a solution is a homogeneous mixture as opposed to a heterogeneous mixture. Homogeneous mixture, you can actually see, you can't see any of the ingredients. Everything looks like it's one thing. In fact, in a water solution, it all looks like it's just water. Even if there are salts dissolved in it, you can't see them. Heterogeneous would be like a mixture of salt and pepper where you can see the individual components. The thing that we're dissolving into it is called the solute. And the material, the substance into which we are trying to dissolve something is the solvent. Most of the time in chemistry, we think of our solvent as being water. But of course, many other things can be the solvent as well. And technically speaking, you can have liquids, solids, and gases as solutes, and liquids, solids, and gases as solvents. And you can dissolve any one of those things into any one of those other things. For example, a metal dissolved in a metal is an alloy, which is a vocabulary word you should know. Obviously, if you're taking care of your car, if you're a driver, you want to make sure your water has antifreeze in it, especially in the wintertime. Antifreeze does exactly what the name suggests. It is a substance, ethylene glycol, that we put into the water, the cooling water in the radiator, mix it around, it depresses the freezing point. So the water, instead of freezing at a particular temperature as you're driving your car, won't freeze until it's much colder than that. And that's very, very important. Interestingly enough, antifreeze also anti-boils. It keeps the water from boiling at a relatively low temperature of 100 degrees Celsius of pure water, but now it won't boil over until it's much hotter than that. And we're going to talk about how much antifreeze depresses the freezing point or elevates a boiling point. And we're going to talk about several other examples of what we call colligative properties. Another colligative property besides freezing point and boiling point is osmotic pressure. And again, that's a little bit later in the chapter. The main point when we get to colligative properties is this, that a colligative property doesn't care so much about what it is you're dissolving, but actually the number of particles, of whatever they are in the solution, because it's those particles that interfere with the crystallization process of freezing or the process of escaping into the vapor state, vapor pressure and boiling, as well as osmotic pressure. Now, how do we measure the concentration of a solution? There are a lot of different ways, and you need to know them all. The way that you're used to so far is by talking about molarity, way number one. Molarity, as you should know, is represented by a capital letter M, and it's a measure of the moles of solute per liter of solution. In other words, we don't have a precise measure of the solvent, it's the overall volume of the solution. And in very, very dilute water solutions, the volume of the solution and the volume of the water are pretty close to each other, but that's not always necessarily the case. We just care about the overall solution. And because that is the case, we can use these volumetric flasks. And we have many, many sizes of these, from a fraction of a milliliter all the way up to multiple liters. And the idea is it makes it easy to measure the volume of solution. The first thing you do is you put your solute into there, and then you begin to add your water. You can grab it by the neck and swirl it around, helping your solute to dissolve. And then you fill it up with water until you get to a little line that is right at the etching in the glass. And that's where you have the precise measurement of whatever it states on the volumetric flask. For example, if this is a 1 liter volumetric flask, this point right here would be exactly 1 complete 1.00 liters of solution. And it's also temperature dependent. And usually these are also marked on the label down here, usually at 20 degrees Celsius, maybe 25. So that's number one. Number two, molality. You might remember this from honors chemistry, but molality is a little bit different. The numerator is the same. The numerator is going to be your moles of solute, but the denominator is different. It's a precise measure of the solvent, but it's a measure in mass, not a measure in volume of that solvent. So, and the other thing you need to remember is so much of chemistry, we are concerned about grams of various compounds and chemicals and so forth, but in this case, we're concerned about kilograms. So make sure you convert your mass of your solvent into kilograms if you want to get the correct molality. Notice the symbol for molality is a lowercase m as opposed to uppercase M for molarity, and it's going to be moles per kilogram. So molarity and molality are usually not the same, though on very, very dilute water solutions, where 1,000 milliliters of water is 1 kilogram, it could be pretty close. Number three, the mole fraction. The mole fraction is exactly that. It's a fraction. And in the numerator and denominator, you have to have moles. The most common mistake students make here is they failure to convert their grams or kilograms of solute and solvent into moles. So make sure that your solute and solvent are put into moles. The other thing to remember is that the denominator is the sum of all of the moles that are mixed together. And then the one that you're trying to find the fraction of goes in the numerator. For example, if you're trying to find the fraction of girls in a room, you would have the girls in the numerator and girls plus the guys, we'll use B for boys, in the denominator. Obviously, if you multiply this by 100%, then you'd have a percentage by mole. Now next, we have weight percent, number 4. I'm going to call this part A because number 4, part B, would be percentage by volume instead of percentage by weight. Now, since all of our masses would be multiplied by 9.8, we actually mean here the mass percent instead of the weight percent, because it's going to be in grams or kilograms, doesn't matter, because the dimensions will cancel. Grams over grams cancel. And most of the time it is in grams and not in kilograms. And notice again that the masses of everything that's part of the mixture goes in the denominator. You can also do this by percentage volume, where everything is going to be in milliliters instead of grams. Now, the last one, number 5, is parts per something. It could be parts per million, parts per billion, parts per trillion. So when you see ppm or ppb or ppt, that stands for parts per million, trillion, billion, billion, trillion. In any case, this is another way of representing concentration. Now you might say, how much do you need to have before something is dangerous? And that has technically nothing to do with any of the values that measure concentration. It has everything to do with, well, what is it that you're trying to dissolve? If you're mixing some fentanyl, for example, into something, you might need and I'm guessing here, parts per trillion or parts per even smaller than that in order to technically kill somebody for this to be fatal. But if you're talking about, sugar or salt, then it's going to be a much, much higher amount before something like that could be considered poisonous or dangerous or toxic. All right, the solution process. Leave it to chemists to say, well, just exactly how does a solution take place? And if you think about a container of water, for example, as a representative solvent, and we start adding some salt to it and stirring it up, for the first period of time that we're adding salt and more salt and more salt, it keeps dissolving because our solution is unsaturated. It doesn't have the total amount that's possible to dissolve in it. At some point, the solution becomes saturated. And this would be different at different temperatures, of course. And how much it takes to saturate a solution depends upon what the solute is, and it also depends upon what the solvent is. But at the saturation point, what would happen is the next bit of solute you add would go right down to the bottom of the beaker because there's no more room in the solution for it to dissolve. What's going on here is that every single particle of your solute is now surrounded by water molecules. And so if you add some more particles of solute, there's not enough water molecules to go around to surround or to solvate those particles. And so those particles then precipitate to the bottom. Now, at the moment of saturation, you're at equilibrium. So we have that double arrows here, or maybe we could even just do this. It means you have not only solute, but you also have the dissolved part. And please remember that this is a physical change. This is not a chemical change. This is not a chemical change. In other words, we are not decomposing a metallic chloride into some other substance. We're not breaking it down by heating it up and decomposing it, or passing electricity through it to get pure copper, solid, and chlorine gas. That's not what we're doing. This is a chemical change. We're talking about a physical change reaching equilibrium. And you're going to see charts and tables to show you the solubility of different solutes in different solvents, usually in water. Next, if we take a look at this picture right here, we have 3 different densities of liquids, and which we have to layer very, very carefully. But then if we shake it up, we mix it up, you're going to see that 2 of the liquids are going to mix together, and the blue copper sulfate is preferentially going to dissolve towards the top in the upper liquid. All right, liquids dissolving liquids. So this is a special case that's just liquids and liquids. Solids or gases are not part of this. And we have this word miscible. If each liquid can dissolve in the other liquid in any ratio you want, we say that the 2 liquids are miscible. If not, then they are immiscible. And the most common example of miscible is ethanol and water. This is the alcohol that's in alcoholic beverages and in oftentimes dissolved in medicines. You can have 90% alcohol, 10% water, or 90% water and 10% alcohol. One dissolves in the other. And so you might ask the question, well, which is the solute then and which is the solvent? And this would be an interesting case that if you're adding ethanol to water, up until you have a 50-50 mixture, the ethanol is a solute. But then after that, where the ethanol is more than the water, then the water becomes a solute. And of course, that's because they're both polar liquids and like dissolves like. Now, when we analyze this idea of like dissolving like in greater detail, we can see that, especially with the case of things like ethanol and water, we have hydrogen bonding going on. And of course, you want to have hydrogen bonding be strong enough to pull apart the ethanol and the water molecules so that they can surround each other and truly dissolve. If your two substances are nonpolar, then you're relying on dispersion interaction forces, your London forces, to be strong enough to mix up and separate the solute particles from each other, separate the solvent particles from each other, and then allow them to totally mix. Now, what's important in this part of the chapter is to recognize that entropy is a big deal here. At some point, we find out that more so than whether something is exothermic or endothermic when you dissolve things is whether you are increasing in entropy or decreasing in entropy. Now, most of the time, the solution process is exothermic when it dissolves. Almost always. There are times when the dissolving process is endothermic and it actually gets colder. And for that to happen, there needs to be an increase in entropy. We'll talk about this a lot more in chapter 19. Sometimes entropy is the driving factor. Sometimes exothermicity is the driving factor. But many times they work together. But when they're working in opposite directions, like an endothermic solution process, then the entropy wins out over the fact that it's not losing heat, but it's gaining heat. And a good example of a supersaturated solution is to use sodium acetate. And this is where you heat something up, you raise the temperature high where it can dissolve a lot more. It needs to be pure water, pure sodium acetate, no impurities, and then you let it cool down, and the stuff that's dissolved stays dissolved. And then when you begin to pour it down and it reaches the contaminants or whatever that's on the surface, it immediately precipitates. And I've had the situation where the precipitate forms so fast, the precipitate goes right up and into the beaker and precipitates and hardens, solidifies inside the beaker before I can dump all of it. I've never been able to duplicate that. It just happened to be the perfect situation. Here's another example of like dissolves like, where we have some iodine dissolved in polar water. And iodine, of course, is nonpolar, but you'd have significant dispersion interaction forces because it's a big molecule. And you have nonpolar carbon tetrachloride down here. Now, when you shake up the tube, the iodine, being nonpolar, prefers to be dissolved in the carbon tetrachloride. And so now, whereas it's brown in the water, in the carbon tetrachloride, it turns a more purple color. And because of time, I am going to stop right here, and we'll pick up on the math part and enthalpy of solution later.